This is worksheet 7 of the States of Matter packet. So in this worksheet and in the next one, we are going to look at some special graphs that help us to talk about states of matter and phase changes. So when we talk about the phase of a substance, if it's a solid, a liquid, or a gas, there are really two variables that affect this. The temperature that the substance is at. So like if you think of ice, right, it's at a cold temperature, you start to heat it up, it's going to melt into a liquid, you heat it even more, it's going to vaporize into a gas. But what we don't always think about is that besides temperature, pressure can also affect the phase of a substance, right? Because the difference between a solid and a liquid and a gas is how tightly packed together the molecules are. So if you apply a lot of pressure to a substance, then it's going to squeeze its molecules closer together, allowing more intermolecular forces to form, and then you're going to eventually, liquefy and after that solidify the substance. So this phase diagram graph that we're looking at here is really a graph of temperature. In degrees Celsius versus pressure in units of atmospheres. Okay, so some things to keep in mind as we look at this graph, just for reference, room temperature is between 22 and 25 degrees Celsius. And then a normal pressure at sea level, like where we're at right now, not on a stormy day where there's like a low or a high pressure system coming in or anything like that, would be 1 atmosphere, ATM, as a unit of pressure. Okay? So some things that you want to notice about the graph. First of all, this is a phase diagram of water specifically. Okay, we can give you other phase diagrams of other substances and they're going to look a little bit different, right? Because different substances have different melting and boiling points, and they're going to be a solid or liquid or a gas under slightly different combinations of temperature and pressure. So this phase diagram is only true for water. If you wanted a phase diagram of carbon dioxide, it would have the same general shape, it'd have the same various regions on it, but the lines would be in slightly different places. Okay, so some important regions to notice. All right, I'll try to point these out in a different color. At the lowest temperatures, you always have your solid phase. And so if we refer back to water, which we're familiar with, that's kind of easy, right? Because at a low temperature, when it's cold, you're going to have ice. That's the solid, right? As the temperature starts to go up, you get to this line that represents where kind of both a solid and a liquid exist, because the solid is melting into a liquid. And so all along that line are various melting points, right? If we want the melting point at a normal pressure, we'd have to look at, okay, well, what temperature lines up with 1 atmosphere of pressure, right? Well, it's 0 degrees Celsius. So the melting freezing point of water, right? It'd be melting if you're going from solid to liquid. It'd be freezing if you're going from liquid to solid, is 0 degrees Celsius at 1 atmosphere of pressure, normal sea level pressure. Okay, the next region we get to as our temperature increases then is the liquid region, which they labeled here as water because we're being specific to water. Okay, as we continue increasing our temperature, we get to this line that represents where you have both a liquid and a gas existing sort of at the same time. And so anywhere along this liquid gas line would be the boiling point, right? Because when you go from a liquid to a gas, you do so by boiling. Now, if you were going the opposite direction from a gas to a liquid, then that would be the condensation point. Okay, so if we wanted to know on this graph the boiling point of water at a normal pressure, right, we'd follow that 1 atmosphere of pressure over the line, and we go down and see what temperature that's at, and it's 100 degrees Celsius is the boiling, condensing point of water. And if you keep increasing the temperature more and more, and also decrease the pressure so that the molecules can move farther apart, then you get into the region that is farthest to the right on the graph, and that is the gas or water vapor region. Okay, so from left to right across the graph, you always go from the solid to the liquid to the gas region, no matter what substance you're talking about. Okay, the other thing that you can find on all phase diagrams, regardless of substance, is something called the triple point. So here is the triple point, and this is a really unique location. For water, they're saying that it occurs at exactly 0.006 atmospheres and 0.01 degrees Celsius. This triple point is the point where solid, liquid, and gas all exist sort of in balance at the same time, right? There's a critical point also, okay, and I've defined the critical point further down here. I'm not going to test you on this, but you see it on a lot of these graphs. Okay, so here's the critical point. This is where the temperature and pressure above that, water doesn't exist as a liquid. You've just got way too high of a temperature, and so you're just always going to have a gas, and so that liquid gas line sort of isn't relevant anymore, right? So those are the main points on the graph, and the idea that we want you to work towards is if we were to give you the phase diagram of a different substance, you could still find these various points on the graph and sort of compare and contrast the two graphs, which is what you will do the next time you come to class.